want to think more about it, let's wait for the next lecture then. Okay, you give your time to think over it. Okay, right. So we can move further now. So we have left with this problem. Okay, and it says that suppose that 5 cards are drawn at random and without replacement from a deck of 52 cards. Okay, assuming that the outcomes are equally likely. Okay, I think this is well understood. Okay, and find the probabilities for the following events. So let's take first event, the event that each card is paid. So this is a finite, I think the sample space is of finite length, right? And then equally likely assigning proper probability is also possible, right? So everything is fine here. So every card, each card has the probability is 1 by 52, right? Okay, that's the meaning of equally likely now. Now, the event that each card is paid, so you are familiar with the type of cards, how many type of spade, how many type of heart, how many type of diamond and other. Okay, so it's going to be assigned in a way of classical definition of probability, that number of possible outcomes and the number of favorable outcomes versus the total number of possible outcomes. Okay, so you have the first answer for the first problem is, I hope all of you can do this problem. So possible number of exhaustive cases, okay, possible number of exhaustive cases is out of 52, your 5 cards are drawn at random and without replacement. Okay, so they have, order doesn't matter, right? So 52C5, that's going to be the total number of exhaustive cases. Now favorable ones are what? How many? So total number of spades are 13. Okay, right? So favorable cases are out of 13, those 5 should come. This is what it means, right? So total number of favorable cases are 13C5. Okay, so this is what the answer for the first problem. Okay, right. Now let's move to the second problem, the event that at least one of the down card is paid. So this is interesting problem. So let me move to the next page. So we want to get the answer of this. E2 is the event that at least one of the drawn card is paid. So it's the event that at least one of the drawn card is spade. And there are could be possibly at most are 5. Right? Now, at least one of the drawn card is paid means one. There is a possibly one drawn card is paid, 2 drawn card are paid, 3 drawn card are paid, 4, 5. The total number of cases are 5 cases. Okay. Now, if I write down the negation of this, means the outside this means what is the negation is E2 complement. Okay, means what is the negation of this? The event that none of the drawn card is paid. Okay, the event that none of the drawn card is paid. Is spade. So this is easy to handle, negation. And what is the probability of, so none of this E2 is, this E2 complement means the negation of this, the none of the drawn card is paid, means total number of exhaustive cases are 52C5 and total number of favorable cases. So none of the drawn card is paid, means they should come out rest of the 39, right? Right? So 39 C5. Now we note that not that this E2, this probability of E2 complement and probability of E2 are related. Okay, by what? So because you know omega, you can write this, if you denote this as a sample space, you can write always as E2 union E2 complement. And you know by the property that E2 and E2 complement are mutually exclusive. So probability of omega is equals to probability of E2 plus probability of E2 complement. So this will give you this relation that probability of E2 complement is equals to probability of omega in a full sample space, that's 1 minus probability of E2. Right? So this will give me the answer for the first. So rather handling this these three cases or 5 cases, I can handle with this very simple one. So 1 minus 39C5 divided by 52C. That's going to be the final answer. So if you know this, if you know this relation, you can handle this easily. So there are 2 ways at least I can look at here to solve this problem, this E2 event. Okay, right. Now let's go back and this is done. So E3 is the event that among the drawn cards, 3 are kings and 2 are queens. I think that also can be handled. Okay, so this is easy, so I can handle it here itself. Okay, so you have still the total number of exhaustive cases are 52C5. Now favorable outcomes. Okay, so you're saying that the drawn cards 3 are kings. So how many kings are there? Total 4. Out of 4 you should choose any 3. Okay, into simultaneous task. Okay, so this is 3 are kings and 2 are queens. Out of 4 queens you should have 2. So this is going to be the answer for this probability of each. Okay, now I think this 4th event can be answered. Okay, I think I can left it to you. Okay, to fill it. Okay, so because you know how many kings are there, how many queens are there, and how many jack are. Okay, they are all are 4, 4, 4. So you can use this simultaneous concept and you can find out total number of favorable out cases divided by total number of exhaustive cases. Okay, right. Now we are going to define a concept called conditional probability. Okay, so far we were working with the case simple probability. Now we are going to make it conditional. Means you have more information also with you. Okay, in the sense that let's take an example, quick example here. Let's take a example of rolling 2 dice together. Okay, so rolling 2 dice will lead to the following sample space. I hope that you will be with me. I comma j, all set of all possible pairs. I can have take value 1, 2, 3, 4, 5, 6, and j also will take the value from 1, 2, 3, 4, 5, 6. So you have rolled 2 dice, and this is going to be the possible sample spaces. In a precise notation you can, okay. Now I'm telling you that the sum on the sum of the dots on the 2 faces is equals to, let's say, 10. Okay, I'm giving you information that, okay, let's even, I'm saying the event that the sum is 8 or 8 is sum is, let's say, 10. Okay, so I hope you can and assume that the situations are fine. Okay, and you have unbiased dices, okay, and all of the outcomes are equally likely, means all pairs will occur with the probability 1 by 36, you can see. Okay, so everything is fair enough here. So I think I can write all the possible favorable cases to E1. Okay, so the event that the sum is 8. Okay, let me write down. So one, whether any pair with 1 will occur, no, because maximum sum 1 comma 6 is, that is 7. Now 2 comma 6 is 8, you know, 3 comma 6 is 9, so only possible is 4 comma 6 and 5 comma 5 and 6 comma 4, right? These are the only possible 3 outcomes which are falling into this. These are favorable cases to this E1. Okay, now it is very easy to find out what is the probability of E1 is 3 by 36. It's very simple, 1 by 10. Right, the sum is a 10, that's probability is 1 by 12. Okay, now suppose means it is given to you that that even event has occurred. Okay, so now I'm defining another event here, that E2, that the first dice shows 5 when the first dice shows 5. Okay, okay, I have this event E2, the first dice shows 5. Okay, so I hope this also, that the set of all possible such events also you can write up here. So it's going to be 5 comma 1, 5 comma 2, 5 comma 3, 5 comma 4, 5 comma 5 and 5 comma 6. Okay, now what I want you is find the probability. I want to answer this question. Find the probability that the first dice shows 5 if it is known in advance that the sum is 10. Okay, so if it is known in advance that the sum is 10, in that condition, what is the probability that the first dice shows 5? Okay, now I hope you know the answer also, maybe, I don't know, but what I want is, like, I want to, so how do you write in mathematically here is, if I know I have defined the events. Okay, I want to get a probability of E2. Okay, given that E1 has occurred. Okay, this is this mathematically written. Okay, so this this bar you can write, you can read it as given. Okay, afterwards that has occurred, already had occurred. Okay, now the one way is you keep on following the step by step, that okay, even has occurred means you have no new sample space, that is a even. Okay, you have a new sample space, that is a even now. Okay, even, not even number. Okay, so it is known that the sum is 10, means that previous the full sample space is no more, the new sample space has come. Now in that sample space, what is the probability that that the first dice shows 5. Now see 1 out of 3. That's going to be 1 by. Right? Now, on the other hand, okay, how will you get this also mathematically? Now, if you, so this is going to be 1 by 3. Many of you have given that answer as well. Okay. Now, if you see, what does that mean is this now, how will you assign the probability is mathematically, what is the definition is probability of happening of E1 and E2 together divided by the probability of the event that has occurred already. Okay, so this is the mathematical definition, provided probability of this denominator should be strictly greater than 0. Okay, that's required to for well-definedness. Okay, now how will it help you is okay, right. So this is the mathematical definition of the conditional probability. Okay, so now let me write down the definition of it's a very the definition of conditional probability. Okay, so mathematical definition is probability of A given B is equals to probability of happening both of the event together divided by the probability which has already occurred. Okay, with probability of B is greater than 0. This is provided this case has. So you can verify now for the previous example, probability of happening E1 and E2. What is the probability? Happening both E1 and E2. So E1 has the pair now 5, 5, which is common to you. Okay. So what is the probability of getting? So this is nothing but probability of getting 5, 5. And that is going to be 1 by 36. And now what is the probability of E1? That we know 3 by 36. Right? So now from here you can certainly find out U2 given E1 is equals to 1 by 36 divided by 3 by 36, and that's matched with your answer 1 by 3. Okay, now another important thing here is, okay, you can look at here this definition of the probability, which is a new definition now. Okay, conditional probability is again a probability function. Of course, that is means depending on the previous probability, you are working on the right side is the probability which is defined already on omega. If I want to show you the dependence, it's depending on the sample space omega. But here, this side is defined depending on the new sample space, that is B. Okay. Now, exercise to you is that it will satisfy all the 3 axioms which the probability, that axiomatic approach has, okay, satisfied with respect to omega. It will also satisfy with respect to B. Okay, that you can verify all the 3 axioms. Okay, all the 3 axioms which you have studied for the axiomatic approach for defining the probability, you can verify that this definition also satisfies all the 3 possible axioms. So that will also that will follow, then it will follow that this will again a probability function. Okay, right? So you have an exercise now. Okay, right? So I'm just saying, so this is an exercise to you that conditional probability function. Okay, conditional probability function satisfies all all three axioms of the probability function. Okay, all three axioms of the probability function or the probability definition, you can say. I must say here probability definition. Okay, and it is again a probability function. Okay, that you should work out. That's very simple. Okay, it's not a big deal. You have to only try to use the fact that the right hand side is a probability function. Okay, right. Now let's move to the note problem. Let's take this example. 6 cards are dealt at random without replacement from a deck of 52 cards. Find the probability of getting all cards of heart in hand, given that there are at least 5 cards of heart in the hand. Okay, so you have okay, it is here there are means you have been given that there are at least 5 cards of heart in the hand. Okay, this is already known. Okay, now in that situation you are going to find the probability of getting all cards of heart in hand. Okay, so if I say even is the event that at least 5 cards of heart in the hand okay, now again here, so at most 6, right? So it is not favorable to go with the negation of this, because if you go with the none, I don't think so. Means negation is going to be at most 4 cards of heart in the hand. Okay, so it's not favorable to go that side. Okay, so probability of even this event, it can be easily find out. So at least 5 cards of heart in the hand. So total are out of 52. See, 6 is going to be the possible means exhaustive cases. Okay, now heart out of so total number of heart are 13. So out of 13, at least 5 means first case is 5 out of heart and 1 is from rest of them. Another case is this is going to be 52 C6 and all of them are heart. Okay, now let's define the E2 event. E2 is the event that the all cards of heart in a hand. Okay, so all cards of heart in a hand. So that's the event now. So probability of E2 is going to be 13C6 divided by 52C6. Now, what do you want now? You want that probability of E2 given that E1 had happened. Now, this next, let's now follow the definition. So, E2 and E1 happen together, divide by the probability of E2. Okay, now this is going to be, you have 13C6 divided by, so happening together, E2 and E1 together means at least 5 cards of heart in a hand, all cards of heart in a hand. So that's going to be, if I go with the this step is going to be probability of E2 divided by probability of E1. You will get the same intersection in E2 in E2 because E2 is a proper subset of E1. Okay, so this is going to be 13C6 divided by 52C6 divided by, you have 13C5 into 39C1 plus 13C6, right? Divide by 52C6, and this 52C6 will get cancelled, and now you are good enough to solve this arithmetic operation. Okay, that final answer I left it to you. Okay, right. Now let's move forward now. I hope if you have anything to say, you can Okay, right. So let's move to the next question, the second example now. Okay, there is an urn which contains 4 red and 6 black balls. Okay, now 2 balls are drawn successively at random and without replacement from the urn. Okay, now find the probability that the first draw resulted in a red ball and the second draw resulted in a black. Okay, so here is a conditional, okay, that find the probability that the first draw resulted in a red ball and the second draw resulted in a black ball. So if I try to understand this situation, okay, so you have an urn which contain 4 red plus 6 black balls. So 2 balls are drawn successively at random and without replacement from the urn. So find the probability that the first draw resulted in a red ball. So successively, okay, 1 by n. Okay, so in a red ball, and the second draw resulted in a black ball. So it's very simple to why to go with the conditional probability. It also very simple and straightforward. There are various ways to handle this problem. Okay, the very simplest way is you have our total number of balls are 10. Okay, so first draw. So when you draw first, then you will draw the second, right? So, but they are happening simultaneous task. Okay, so you have first drawn ball is red with the probability is 4 by 10 into, now that ball is drawn and is not replaced. The second drawn ball is black. So still, so first drawn ball is red. So what is the probability now out of, now how many balls are there total? 9. So 6 out of 9. So total number of favorable cases are. Right? So you have, this is now you simplify it, you can have you can, right, you can simplify it. So you have, this is 4 by 50. Okay, so how will you look? So if I want to, so it's since it is I don't know how this has come into this case. Now can we model it in conditional probability case? So that also you can look at. Okay, that way also you can look at that first drawn ball is red. Okay, so you can make the case that probability that the first drawn resulted in a red ball. What is the probability that the second draw resulted in a black ball? Okay, so find the probability that the first draw resulted in a red ball. Given that, you can say, okay, for that case, I'm just reformulating this problem. the last two lines. Okay, so given that the first drawn ball is red, find the probability that the second drawn ball is black. Second drawn ball is black. Okay, so it is given that the first drawn ball is red, so second can be also red, and second could be black. So you can distinguish these two cases, right? And you can find out the. Okay, so this you can have the sub case. Okay, so it is, see, this when 10 C2 or C case, or when without C case. Okay, it's depends on the problem. You have to understand the problem, how it is, means how, means what it addresses. Okay, means it is means you have drawn successively at random, means one after the other. The first ball drawn, then second ball drawn, and one is you at a time you have taken two balls out. Okay, so there is a, so here is the here is the clue. Okay, that if you drawn two balls, means you drawn two balls, means it should be clear from the example. If it is not clear from the example, you can't do anything. Okay, or you have confusion, with confusion you have taken this. Okay, all of them are together, let's do in this way. Okay, so but here it is clearly written that it's not drawn successively, one after the other, at random and without replacement. Okay, so it is not like you have put your hand in the urn and two balls you have chosen and take it out straightforward. No, you have taken first ball, then you have taken second ball. So there is no C case now. Okay, right. Okay, right. So now let's have one more problem. Okay, so a bin contains 5 defective, 10 partially defective, and 25 acceptable transistors. Okay, so again you can understand, I think this problem is well understood. A bin contains 5 defective, means which are, means you cannot work with them. Okay, transistors. 10 partial defective, that may work or may not work. Acceptable, they are fully working. You can see how, this is how you can look at it. Okay, so a transistor is chosen at random from the bin and put into use. So it could be a possibly either defective or partial defective or acceptable. Okay, so if it does not immediately fail, suppose it is given to you, if it does not immediately fail, what is the probability that it is acceptable? So it does not immediately fail means what? So if you try to answer in a one line without looking at conditional and all, it's a one line problem. Okay, now if it does not immediately fail means that it will be that chosen transistor only possibly either will be partial defective or acceptable. It is not going to be defective. Okay, so now you have a new sample space, like you have total 35 transistors, out of which that transistor has been chosen. So what is the probability that it is acceptable? So it is, so favorables are 25. So out of 25, if I want to give a one line answer here, it is going to be 25 out of 30. Yeah. Okay, that's going to be the final answer. Now, if I try to model it in terms of conditional probability, so let's take if it does not immediately fail, what does it says now? Okay, so let's take E1 is the event that chosen transistor, okay, transistor does not immediately fail okay, and let's take E2 is the event that it is acceptable, so chosen transistor is acceptable. Is acceptable. Now suppose, see, you can now let's take, see, defective, you can make it D1, D2, D3, D4, D5. Partial defective, you can say PD1, PD2, PD3 and so on, PD10. Similarly, acceptable, you can make it A1, A2 and so on, A25. Okay, you can name them. Okay, now it can be easily seen that E2 is going to be a proper subset of E1. That can be seen once you analyze that. So now what we are looking is probability of E2 when E1 has occurred. So if you apply the mathematical definition, it's going to be probability of E2 and E1 happen together divided by probability of E1. That's going to be probability of E2 divided by probability of E1. Now, chosen transistor does not immediately fail. So how many number of favorable cases for this case is, so probability of E1 is going to be total number of means who may not fail or will never fail. So 10 and 25, so total 35 out of 40. So that's going to be 35 out of 40. And probability of E2 acceptables are 25 out of 40. So you are having now 25 out of 40 divided by 35 out of 40. So this is going to be 5 by 7. Okay, right. Let me see your questions in the chat box. See, I can see your question. Wait a minute. Let me see your question now. Shubham, you have put it doubts that what is the difference in two events, taking red ball then black ball and taking black ball given that red ball is taken. See, you have see, it is if you go back and here, so the first draw resulted could be result in either a red ball or a black ball. Okay, and second draw also can be resulted in a black ball or red ball. Okay, that's so first draw, second draw. There are two draws happen. Okay, now you are saying that difference into taking red ball then black ball. Okay, and taking black ball given that red is taken. So see, here you are making like taking red ball then black ball, and taking black ball given that red ball is taken. I both lines are almost the same thing. What I can understand. So taking red ball, then black ball. See, if it's a very huge class. It's you because if I unmute everyone, it is will be very difficult to manage. Okay. Let me give you permission now. Okay. Unmute yourself and give.
Yes, sir. I had one doubt in this slide. Sir, we solved this second example by different method and the first example by different method. But there was no difference in the type of question. Means in both question we are picking up things without replacement. So in first question also our sample space decreases, and in second question also our sample space decreases. So why did we
See
change the
here,
method?
what one thing. So 6 cards are dealt at random from a deck of 52 cards. See, there is a see here. Yeah, you carry on. Let me understand you.
Yes, sir. So we didn't use the NCR method in second question, but we used the same method in first question.
Huh.
So what? Why did we change the method?
See, that is here. See, I here if you see implicitly, it is see out of 4, how many are there? 4C1 out of 10C1. Okay, so first draw will take 10C1 only. Here is 4C1. Okay, now here is 9C1, right? And out of 6C1 here. So it's only second draw.
But sir,
Did you get?
after we are taking means we are if we consider like for first card there are four options, and for second card there are six options. So why can't we do 4 into 6 by 10c2?
Wait a minute. Yes, tell me what again? This is the
Sir,
only one case, right? 4C1 and 6C1.
yeah, means for first card we have for first ball we have four options, and for second ball we have six options. So why can't we approach by 4 into 6 by 10c2?
Just a second. See, I see here. I have drawn successively one after the other. That's a meaning here. Okay, here we have not drawn it successively. Okay, did you get my point?
Yes, sir.
Okay, they are drawn. You can read this as one after the other. Okay. So there is a difference in both the questions. Okay, for the first case, the total number of exhaustive cases will be different. For the second case, second drawn ball, the total number of exhaustive cases will be different. So that is why here 10C1 and 9C1.
Yes,
Or
sir.
sir, here in denominator we can also write 10p2 because order is important. So
Huh?
sir, here we are choosing balls successively. So in denominator we can also write 10p2.
So what
Right?
is 10p2? This
So
is
we
what
are
I think, 10
selecting
into
two
9.
balls from 10 balls. In here order is
10p2 is
important.
nothing but 10p2 is nothing but 10 into 9.
Yes, sir. So that's
Huh.
what I'm. We can also write denominator as 10p2.
Yeah, so see, these things need to be used very carefully when you are trying to understand the problem of improbability. Every time, whenever you are reading the question itself has the answer, and it's a one-line problem. Most of the time, so far, it's like till we do go for till Bayes theorem, you can say the last result. Afterwards, we will handle the random variables and so on. Till that level, at least, I can say this is a 1 to 2 line problem. If you really understood the permutation and combination, then. Now, I think now this doubt is clear.
Yes, sir. Yes, sir. It is clear.
Okay, can we go now forward?
Yes, sir.
Okay, thank you. Okay, now we had answered this now. Okay, I think here is no doubt, right? Okay,
Yes, sir.
fine. Now let's move to a very important result in probability, which is known as theorem of total probability. Okay, right. So it's see, whenever you are making some pair, if you have done somewhere vector space or something, okay, means vector space means like it's a set assigned with some operations and it satisfies certain properties, then you write a pair and that we call as a some vector space or other inner product space and so on, if you have encountered with them. So similarly, if you have a sample space along with the that probability function, if you write this pair, and this is this I have omitted because of some reasons. Okay, so if you do so, this is known as a probability space, so don't give this much importance right now here. Okay, so omega comma p you can try to understand like a space, okay, where you can work with the probability function. Okay, and so let's take this EIBA countable collection of mutually exclusive and exhaustive events. Okay, such that each probability of each EI is greater than 0 for all I in that index set. You can say this is index set from where I is coming, or in other words, you can write E1, E2, and so on, En, and so on. I you can take this index set. You can take set of natural numbers. Okay, but right now we don't have anything, okay, because it may be countably finite, it may be countably infinite, so that's why here index set is more properly. Okay, then for any event we have the following, and it's very easy to follow if you really follow the definition of axiomatic approach. Okay, so if this is again it 2-3 lines here, I can write this E. Okay, before writing E, I know that.
Sir, can you show the
this,
previous slide once again?
yeah.
One second. Done. Thank you, sir.
Okay, so this is here. So first thing is this omega, that's a sample space. I can write as union of EIs. Because it's saying mutually exclusive, it has some other meaning, but mutually exhaustive. Yes, exhaustive events means you have omega, you can write as a union of all these events. Okay, then we say if you have let's try to understand. So you have an omega sample space, and you are defining by events are certain events. These are mutually exclusive events. Okay, you can say, okay, right? So these are E1, E2, E3, and so on, En. and so on. So total union will define the whole sample. These are exhaustive as well as exclusive for a finite case, you can say. Okay. For infinite case also you can give as many partitions. Okay. In other words. Okay. So exhaustive means it's clearly union EI of a sample space. The second thing is mutually exclusive means you take any pair of events from this set, their intersection is a null set for I not equals to J. That's the meaning of you have this is a exhaustive case. Okay, exhaustive, and this is mutually exclusive. Okay. Now you have event E. You can write event E as E intersection with the whole sample space omega. It's very simple to prove this result. E intersection omega is nothing but union of EIs. And if you really know the relation between intersection and union, and you apply the De Morgan's law and distributive law together, okay. So I think distributive law, okay, not De Morgan's law. So it's going to be you take union, you take intersection with each member, and then take the union. Okay, so E intersect with EI and then take the union. Both will be the same thing. Okay, now this is E equals to, now union of I belongs to the sum index lambda, and this is let's say this is a BI, where BI is E intersection with EI. Now you can verify that BI intersection BJ is a null set for I not equals to J. Okay, BI intersection BJ is a null set for I not equals to J. So what it tells you that these events, new events, okay, which are created by taking intersection of E with respect with EIs, okay, are mutually exclusive. Now if you apply the third definition of axiomatic approach, okay, this tells you that probability of E is nothing but summation of I belongs to the sum index lambda probability of BI. Countable collections of mutually exclusive events. Now, what is BI is summation I belongs to sum index lambda probability of E intersection E. Now, if you write down this in terms of conditional probability, since probability of EI is greater than 0, okay, that is given to you. So now note that probability of E given EI is equals to probability of E intersection EI divided by probability of EI. So this will implies probability of E intersection EI is equals to probability of E given EI into probability of EI. Now these two together will lead to this theorem, okay, this final result. So that will tell you that probability of E is equals to summation I belongs to the sum index lambda probability of E given EI into probability of EI. Okay, right? Now let's try to understand it by an example. Okay, and it occurs with every problem. Okay, every problem which you have seen earlier also, there is a implicitly this theorem of total probability is applicable. Okay, now let's try to understand by an example. Let's take two urns. Okay, let's take two urns. Okay, let's say this is urn 1, this is U1, and this is U2. Okay, let's say there are let's say 4 red plus 6 green balls, and here are let's say 3 red plus 5 green balls. Okay, now you are here and flip a coin. You flip a coin. If you get head, you will go to the urn 1. If you get tail, you go to the urn 2. And then draw a ball. Okay? You understood the situation? Now you have 2 urns which has some type of red and green balls in each cases. You are flipping a coin first. Okay? And if you are getting head, you are going to earn 1. If you are getting tail, you are going to earn 2. And then draw a ball. Okay. Now you are interested in the probability that, okay, that the drawn ball is red. Drawn ball is red. So if I define the 2 cases, first I have to define E1 and E2. Select on U1, and let's take E2 is the select on U2. So see, there are 2 possible cases. Either you will select on 1 and on 2, means you are, if you are getting head, you are going to select on U1, and if you are getting tail, you are going to get select means on 2, and you can certainly tell what is the probability of E1 and what is the probability of E2. That is going to be, they are equally likely. You are taking an unbiased coin and you are selecting them equally likely now. Okay, you can make this case more interesting by rolling a dice. You are getting an number 1, 3, and you are getting 2, 4, 6, or 2, 4, 5, 6. Then you are selecting 2, and so on. You can make this case more interesting. Now, in that case, I want to get the drawn ball is red. So, what is the theorem of total probability says is probability of the drawn ball is red is going to be probability of E when E1 has occurred into probability of E1, selecting the U1, plus probability of E given E2 into probability of E2, selecting the one, because you may go with the any case. Okay, so if you follow this chart, you will get head with the probability 1/2, and then you are selecting the ball 4/10, right? Getting the drawn ball is red. And here is also 1/2 into 3/8. So they are simultaneous. These are simultaneous tasks, but they are not. So these 2 tasks are not simultaneous. So here is a plus rule and here is a product rule. So 1/2 into 4/10 plus 1/2 into 3/8. Okay, so this is what is happening here. So it's going to be in case of E1, so it's going to be 4/10 times 1/2 plus you have 3/8 times 1/2. Now you are intelligent enough to I think solve this problem. Final answer you can write it. Okay, so here the theorem on total probability takes place. So you can, I have told you, you can make this case more interesting by flipping or by rolling a dice, rolling a pair of dice, and you can make more urns. You can select more urn and so on. You can make many cases. Okay, you can generalize. Right now, let's this example you can find out in that that video, okay, which is available on YouTube. So this example you try to solve yourself. That's it. That's a very, again, I think it's working with the pair die. Okay, that's what I told you. There you will find the answer as well in that video, YouTube videos. Okay, right. Okay. Now let's try to conclude this lecture by addressing the Bayes theorem. Okay. So let's you have a probability space and see why this Bayes theorem is required. You can say, see, if you in the previous example you have first flip a coin and you are drawing a red ball with you are trying to identify the ball is whether a ball is what is the probability that the drawn ball is red. But now suppose it is given to you that the drawn ball is red. In that case, what is the probability that you have selected on 1 or you have selected on 2? Okay, means instead of probability of E, now you are trying to ask the question that what is the probability that on 1 selected given that E has already occurred. Okay, so this is a kind of inverse problem. Okay, means on 1 selected means you have got the head, you have got probability of getting head. Okay, right? So this is what you have to answer by the Bayes theorem. So Bayes theorem is again it has all the similar statements. Let omega be P be a probability space and let this EI be a countable collection of mutually exclusive and exhaustive events such that probability of EI is greater than 0. Then for any event E with probability of E greater than 0, this is. So this is nothing but this if you look at the denominator carefully, this is nothing but the this is nothing but the probability of E, and it is replaced by the theorem of total probability. And numerator, if you look carefully, this numerator is nothing but probability of E intersection EJ divided by probability of E. So if you rewrite this in the case, so the numerator if you write in the form of in the form of conditional probability, you will get this answer. Okay, the numerator. Denominator is nothing but the total probability. Okay, probability of E given EI has happened into probability of EI, and then summing up all the possible cases, that will be the total probability of E, and the numerator is this. Okay, now let's try to answer the same question, okay, which we try to answer here. Okay, so let me address here. So you have this is I'm interested in getting probability of E1 given E. Means now I can apply the Bayes theorem. So probability of, so or you can say it's a you can apply the conditional probability definition now. E1 given E divided by probability of E. So that is nothing but now see I have to transfer my knowledge in the known things. Okay, what I know is, see, what I know is probability of E given E1 is equals to probability of E intersection E1 with divided by probability of E1. So I know all this stuff. Okay, so from here probability of E intersection E1 is probability of E given E1 into probability of E divided by probability of E. Okay, right? So now this is nothing but probability of E given E1 time probability of E1. Probability of E1, probability of selecting on 1 is 1 by 2. Probability of E given E1 is nothing but the 4 by 10. Drawn ball is red, so 4 by 10 into 1 by 2 divide by this. If you solve it out, it's going to be how much? This is going to be it's 80 and 16 plus 15, so 31 by 80, right? Yeah, so this is going to be 31 by 80. Now you can So 4 by 20 into 80 by 31. So you have 16 by 30. That's the probability of selecting on 1 by using the Bayes theorem. Okay, right. Now, Bayes theorem, I have also solved these examples in that YouTube video. Okay, that lecture number, I think 3. Okay, axiomatic approach, which has discussed all these many problems. Okay, so you can look at them. Okay, and try to see if you are getting any doubt there. We will try to address. Okay, then in the next lecture. Okay, if you have any question, you can ask.